All right, our project is dubbed Intelligent Parking. So this is our overview of what we're going to talk about today. We're going to start with an introduction of our team, and then we're going to go to the problem outline, solutions we talked about, and the actual solution we chose, the requirements, a testing plan, the timelines, the cost of the project, and also the references we used for this information. So to start off, I'm Sean Potter. I'm the project manager. I'm also going to be the software lead, and I'm a computer engineering major, and I did the database research as a background.
Oh, sounds okay. Hi, I'm Nick. So I'm going to be the hardware lead, electrical engineer, and I did sensor research.
My name is Leslie Booth. I'm an electrical engineer, and I did all the research on wireless communication.
My name is Michael Mattis. I am a computer engineer, and I did the research for web applications.
Unity, the electrical engineering, and doing the power supply for our project.
Okay, so why intelligent parking? Here's the big picture. We've all been in the situation going to like a shopping mall or a sporting event, and like just get stuck in traffic and people can't park, and it's awful. And there are more cars on the road now than ever, and it's just going up. So we want a smarter way to park. So we're motivated to solve this. We're parking pretty dumb right now. There's no like mass smart parking that we found. There are a few small, like a few places that tried doing it, but nothing like I haven't seen it actually. So who's going to be affected by this? We have a smart parking system, obviously the drivers, us. The parking garage owners, it's going to be easier on them. And places like shopping malls, you're going to get people in sooner, they're going to be happier, you know, it's in their benefit too.
So there's current solutions out there, broken down into 3 categories. Valet. Siemens is a brand that does multiple people use this approach as a solution, and then smart parking. So valet, everybody knows valet. They come and they either drive the car for you, or at sporting events they lead you where to park. This is like a normal way of approaching the problem. It usually is for short periods of time, so it's like a rush hour dinner or for a sporting event. The next one is the Siemens approach. So multiple companies have this as their design, and what they do is they have these signs in the parking garages that point you which way to go. So they actually have these physical devices, and they also change based on which parking spots are open or how many cars go in that area. And smart parking is the closest to the intelligent parking that we are proposing, but it's a company that serves Australia, UK, and New Zealand. So they have these discs that they build into the concrete, and they keep them underneath, so it's in the middle of the parking spot. So when the car drives over it, it senses that it's there. And it has an application that links to the devices and sends in user information parking spots. The only issue is that this is these are the reviews for the application, and we've done very good research on this, and the application does not work as it's supposed to. People are saying that I drive into the parking spot and there's a car there. There's all this other stuff, and you can tell that's UK because it's rubbish. But that's the main concern, was the actual use of this by the users. So the pros and cons for each one of these. Pros for valet is it's accurate and easy to communicate with because it's humans. The cons is it's very expensive to pay all those people that are working at that place. There's constant supervision, and there's not always efficient parking. They don't know the best ways, they're just going off of what they can see as an individual person. Pros for the Siemens approach is that there's on-site signs and external directions, so there's no distraction being in the car. The cons is that there's no individual experience and not modular. So you actually have to design your parking garage around this. Smart parking, the pros is it's mobile, modular, and city adaptable, but the cons are that you have to have the pro installation, putting it into the concrete, so when you design your garage, you also have to design, we're going to be putting these things in the center of each parking spot. Externally maintained, so the company actually does not allow anybody else to maintain it except for themselves, and it's a constant cost, because over time, you got to keep paying paying them to come back and fix the product or for the new updates. And it's a very, very poor quality app. So this is where intelligent parking comes in.
Because we don't have like we don't have the similar parking system in United States. The smart parking does only exist in UK and New Zealand, right? So we create a new one based on fit our customers' need. We decide that people can use easier, and we use Wi-Fi communication and cheaper detective device make this project economy viable and assist with people that are benefit around all the city.
So for our product, we don't actually have anyone sponsoring us. So to come up with the marketing requirements, I looked up online surveys based on what someone wanted to see in a product such as this. The survey was done and showed one of the 4 base complaints people have with malls is difficulty finding parking. So for the market requirements, I decided that it's important that the system is not intrusive to shoppers. This is meant to enhance your parking experience, not to take it. It's also important that this is easy to install, doesn't cause traffic, there's no accidents. This should cut down on those problems. The information must also be relayed quickly, efficiently, and safely. We don't want distracted drivers who just have to sit on their phone for minutes at a time. This should be a very quick process. The system also has to be reliable and durable. We don't want it breaking down in colder or wetter months. We don't want a little bit of flooding to just completely destroy it. It also has to be easy to maintain. There are a lot of different parking spots in the mall, so we don't want there to be an issue where there's too many and it takes days to like go through. So we broke that down into the objective tree of our overall goal. Our goal is to design a system where the sensor will determine the spots in the parking garage. It'll connect to a database and send that information to drivers trying to park. This will increase overall productivity and improve parkers. It has to be accurate. Information will only be recorded correctly, safely, and make sure everything is right. The maintenance has to be simple, easy to install. You just place it and make it. It has to be durable. It has to survive in harsher weather conditions. And also, obviously, it must be safe. We don't want there to be legal issues or accidents. Which takes us to our engineering requirements. In order for our product to consider success, these are the different goals that we're trying to meet. Our system will give accurate and proper information. The information will be relayed to drivers in milliseconds. The database will update itself at regular intervals about 2 to 5 minutes. It will be safe. Our interface will be very simple and easy to use. It's not going to take long for people to do it. There won't be decentralized phones. The sensor will place down intrusively. It'll be durable, survive multiple different ranges of temperatures. It will be waterproof, and it'll be easy to maintain. Which takes us to our engineering trade-off matrix. Now, we're going to have to make different choices in terms of finding a balance between our market requirements and our engineering requirements. A negative sign means that we want this to be low. For example, for power, we're aiming for low power. A positive sign is that we want this to be high. For example, we have plus for accuracy, we want high accuracy. An arrow going up means that there is a positive correlation between these two things. For example, low power for engineering requirements is a positive relation to low cost. So there's an arrow going up for that. For things where they conflict means that, for example, accuracy has 2 down arrows in the cost column, meaning that for high accuracy, we're going to have to increase the price.
So these were our first kind of approaches, our first ideas. Pressure pads weren't very durable. We did research on a bunch of these. The pressure pads weren't very durable. The RFIDs weren't very accurate. The video camera system would be too expensive, and a laser system would take too much power. So our approach, we want to put some sort of sensor that meets all these requirements within one of those 6-foot parking blocks that you see, with like dedicated spot, one of those plastic pieces. And we want it to be modular in a way that it's a standalone piece. There are no wires running to it. You don't have to build a garage around it. You can just buy these things, drop them down, set up a system like online, and you're good to go. So the problems we're going to run into are going to be, we're going to run into weather problems. We're going to run into the ability for each one to communicate wirelessly. We're going to have a battery system to keep them alive for a long time. And then some other things we might run into are like, what is the cost going to be worth it with just this information? Can we do more with this information?
I'm going to be doing the system design description. So the first thing that we're going to look into is the functional part of it. And so the first portion that I'm going to look at is the level 0 and level 1 of the functional composition. This is going to be level 0. Level 0 is the most basic level. And what we're going to be looking at is the block as a whole. And so our inputs, we're going to presume to be using a battery. And we're going to be sending out from the sensor a sound pulse wave, and it'll be received back. And what's going to be output from the block is a voltage level that corresponds to this pulse wave. And we're going to make it so that that voltage level corresponds to 1 or 0, and that'll tell whether it's filled or not filled. At level 1, there's going to be a little more detail to the parking block. And so the sensor's going to be there, that's always going to be there. And there's going to be the possible inclusion of an ADC. And so what occurs with the ADC is it takes the output of the sensor and it'll give it a binary representation. This binary representation, it's more useful for electrical components because it's easier to process data with a binary representation than it is voltage. The last component is the Bluetooth module, and this is how we plan to communicate between all the devices within our system. So from parking block to parking block, or parking block to the eventual master Raspberry Pi, which will eventually be output to the web application. The input to this Bluetooth module is going to be the binary, and with outputs 0 or 1 that goes eventually to the web application. What follows are the block diagrams. The first one is going to have to include the ADC, and this, we're not sure if we're going to include it yet, but I assume we will. And the second diagram will not have the ADC, and you'll notice that. And so this is going to be the behavioral description of the system. The first one is going to be a specific use case. We've designed several, but this is the most important. And so we have three actors in this use case. We have the passenger, we have the database, and we have the web-based application. And what occurs in this specific use case is that the passenger prompts the web-based application for a map, and then the database just produces it. The activity diagram is what the consumer has to do on their end in conjunction with our system, right? And so what ends up happening is that they'll look up the specific parking mall that they're going to, and then they'll get the map, and that'll display all the empty and refilled spots. From that, the passenger, and we assume it's the passenger because we don't want any drivers using this. The passenger will help the driver find a spot, and then the driver will drive into it and take this spot. The interaction view is a description on between objects within the system. So we have 3 here, and this is going to be the passenger, the web-based application, and the database. So it starts from the passenger, and the passenger connects to the web-based application. From there, the web-based application creates an inquiry, and that gets sent to the database. The database will then respond with 2 things: the layout of the parking map, and then the spots that are filled. These 2 in conjunction will actually output the parking map for the passenger to use. And the final diagram that we want to be looking at is the physical view. And this is the object and software files that are associated with this physical view. And so we have the passenger who accesses the web-based application through browser files, and then this will prompt the web-based application to use the application files, and then the database will use the map files, and it'll just go in reverse so that the passenger will eventually get the map files.
All right, so for the design of this complete project, we broke it down into 4 main components. The parking block itself, the physical device, the controller that controls multiple parking blocks, it'll have access to multiple parking blocks data, the database, and the application which store the information and present that information to the user. Each one of these have their individual tasks, so to say, but we'll get more to that through the timelines. So this is the timelines that we have proposed for our project. Now, I used the Gantt chart to lay out all these tasks that we have lined out. I couldn't put the timeline next to it or else it wouldn't be able to be read, but as you can see that we have tasks built for all of these applications, different parts of our project. And they even work in conjunction with each other. So as we're building the parking lot, we could also be working on the database as well. And we have it broken down into more like a hardware side of things and software, and they do overlap with who's working together. So the hardware team is going to be Nick, like you, and Ewan, and then me and Mattis will be working on the software. We will be working through the winter break, as you can see with some of these dates. I'm just going to show you the actual graph-looking view, so it gives us more like an in-depth. The green is the parking lot, the blue is the controller, red is database, and yellow is the application. And the pink is actually what we're going to use as our testing. So our testing doesn't really begin until in January, because that's when all these things are coming to sort of like a testable phase in their development. And also, as you can see, December 12th we have as our go no-go milestone. And I'll go over what we have to get done to get to that point. Here's our resource chart. The red, so you can see that there's people that are overlapping in what they're doing. So there's going to be some sort of communication to the green and red and the blue and stuff like that. So this is where everybody's projected to work for that entire period. So the go no-go milestone. We have 3 basic parts that we want to get completed. We want to make sure that our circuit, actually we have a circuit and a physical diagram of what our parking block is going to be like. So when we get the actual money to fund the parts, we could actually have a design ready to go, so we can just put it together. So that will be complete. Also, we'll have the database set up complete with the actual database, and also test it out with some test values to make sure that it actually corresponds. And also, we will begin the application. What I mean by begun is we'll have each page, the skeleton of each page, but not have actual details for what is going on in each page yet. So to get there, for the parking block, these are certain tasks we have to complete to get to that milestone. So for the parking block, the first thing we have to do is the part specification. And that's what we've been going over for the past, we started it on the 14th, and we've been going on since then. So we're trying to figure out what parts are going to be used for sensor-wise, for battery, for all this other stuff, and what would actually be a beneficial use. So after we get those parts, we're going to go into the design circuitry phase. And actually, let me go back one. So the people working on this, the bold name is the person that's leading that. And so if that person, like, he's getting sick right now, he can't complete that task or lead that task, the person right behind will jump in and take that leadership role and position. And that'll also be the communication to me as the project manager of how these tasks are being completed and where they are in their status. So the parking block, Ewan will be in charge of the actual design circuitry phase. He'll have that access. So the predecessor to that would be the parts, because we can't design the circuit without having parts. And then the design layout. So after we have the circuit, we actually have to make this into will it fit inside the parking block? We have to design that sort of phase to it. And Nick will be in charge of that one right now. Now the controller design. This is also going to have some sort of physical design to it. And also the circuitry design. So we'll need the actual specs for this controller. What are we going to have as the parts and stuff like that will be decided in the parts phase as well. Communication design. How the controller will communicate with the database as well as the parking blocks. So Michael will be in charge of that, and he'll also be communicating with me and Mattis as well. And we also are thinking about actually talking to Mauro and Horan to have their expertise in their respective fields, with Horan with the connectivity of network connectivity and Bluetooth with Mauro. The database design, that'll be designed to satisfy the third normal form, so that it's actually a efficient database as well as properly standard met. I'll be leading that. Also, after we have a design for the database, we go into the construction phase of the database. And this will actually be for the skeleton purposes, because the data that actually is going to be put into the database will be coming from the parking blocks. But we will also test out that we could actually insert some data and find out if it does meet our standards. So the application. So for the application, we're going to have a universal app that'll be used for both Androids and iOS devices. Since we haven't done any programming in that field, that's why this duration for the design of this is longer than it should be, because we have to do research on actually what can we do, and then put it out and say, okay, this is what we're going to do. And after we get this design and we get all this research, we'll go into the building of the application phase. And this is going to be, as I mentioned before, so when I said begun, it's going to get the skeleton, but the skeleton's got to be done, but it's not going to be stopping there. We're going to be moving on right into detailed pages. And once we get the skeleton, that'll be easy to break it up into who's working on what page at what time, and there's going to be communication between how those pages interact with each other. So then after we do that, we'll have a testing plan.
First, we will do the individual tests of each block to test the sensitivity, if it works for cars, or if people walks around, if the sensor detect the people as a car or something. That's the first step. And the second step is the connectivity test. It's like whether the sensor detect the information sent to the computer correct or not. Sometimes there may be an interaction to cause a wrong data sense. And then we do a group testing to test 2 or 3 sensors putting together into a system and make sure the system works. And then we try out what the error is, then that's basically the whole text.
So this is the cost estimation page, and these are pretty much fixed prices of all the hardware components that we really want to include, or roughly around in that range. And so roughly it comes out to $100 to $130 per parking block, but that doesn't include the controller that we want to add, and that eventually came out to a full $300.
Yeah, so like it doesn't include like the 130 is just for the individual parking block. For the entire test system, which is going to include, we're going to actually make another sensor, but not include it into a parking block, because we'll just have it as a proof of concept that they do interact with each other. And then that's also included in the price.
Right. And so that's why it comes out to $300, and it doesn't seem like it really does. We're going to be depending on the $300 allowed from the stipend from Manhattan College. And I didn't really put worker hours because I didn't really want to guess at it. And I know that everyone's going to be working very hard on this project. And the thing in the tiny font with a little asterisk on it, it pretty much says that the cost is fixed, but there's definitely, like, we could include like other functionality, which could mean the inclusion of different hardware prices, which could definitely increase the price of what we're looking at.
And so these are the resources that we use, like when he was talking about the survey. Actually, that survey was done by UPenn, so we were actually really happy to find that. And also this has the sources of some of the sensors and some of the prices that we got, as well as where I got the reviews from the smart parking. So does anybody have any questions?
So you have your modular parking blocks, one per block,
Yep.
and you have a main hub that will integrate all those blocks?
Yes. Yes.
What is the reason that they also communicate with each other?
So when you have the parking blocks communicate with each other, it'll send down like one strip. So it's, you know, when you have parking, you have one strip of information. They'll communicate with each other to send one string to that controller, instead of having each one trying to access the controller. So it minimizes the connections to the actual controller device. So it'll be like a hopping mechanism where it attaches the string, and then you'll have the actual.
That
answers my other question
like
too.
distance, or like a garage that has weird turns and it's all concrete, rather than having a relay kind of every turn. You can have the blocks talk to each other around a curve or down a lane. And
As
then
long as you get one of
end,
them, you can.
right. The
you
one
can
at the
have
end
those.
knows
Exactly.
all the others. You can jump to the.
So you mentioned you're going to use like binary numbers to represent
Yes.
communication between the parking spots. If you have them communicating together, the spots, is it going to be like a binary string sent to it?
Yes. Yes. So it's gonna have a one string sent to it, and then that's gonna be processed by the. So it's gonna be processed by the controller and then sent to the database. where it's going to line that all out. And what will happen is there's going to be, in the processing phase, it's also going to count as like, maybe it gets it'll get a 1 for a quick second and go away. It'll process that out so it doesn't take any false positives, as Ewan was pointing out, like if someone's standing in front of there or something else like that. And the benefit of us actually having this parking block that we actually didn't talk about is because the smart parking, one of the biggest issues was that it wouldn't pick up a signal if it wasn't right on top. So like when you have the park, like you're gonna park a motorcycle to the left of it, you're not gonna get anything there. Everybody hates when they pull into a parking spot and they see a motorcycle right there. So like that's like another benefit of our presentation.
What kind of features are you looking for to have on the application?
So for the application, we're going to have a, so that the user looks at it and can say, okay, this is where the parking spots are, and it's also going to load in the actual parking garage layout. So it'll have like, so for Manhattan College, it'll have, okay, there's 4 floors, there's 5 floors, and it'll tell you which floor to go to and where on that floor are there open parking spots. So we're gonna have that as a user interface as well as the reserving. So if you're going into a parking spot and you're like, okay, I know I'm in the 4th floor, and you start looking for that parking spot, you reserve that so nobody else can access that parking spot or get sent to that parking spot. Of course, there's been people that are not using the application that might go to that parking spot, but that's a small use case that we have to.
This could be like specific lots, like a mall could put in specific, like only these app users use, like can reserve that, so it's a lot easier for them. And maybe like a more ambitious idea would be, imagine you had a smart car that you could drive up to the mall, get out at your store, and have the car somehow integrated with this app that it knew where a spot was, and then was able to like go valet itself. And you went in, you're coming out of the mall, and you press on your phone, and it comes and picks you up.
So, yeah, especially with all the Tesla coming out here with this new smart technology about this.
So device-to-device communication, you guys are using Bluetooth?
So for the actual parking blocks, we're using Bluetooth so that they can interact with each device because it's got to be one-to-one. But for actual the controller, we're going to be using Wi-Fi and internet connections because even most parking garages already have that for the security features.
Right.
So we're going to tap into that and use that as their.
Did you guys decide on a wireless protocol yet? Or
No, we're just in the basic phases of setting this up. Yeah.
You mentioned that the parking blocks are supposed to be wireless, so they're going to be run on batteries, I saw.
Yeah.
How are you going to overcome that need of eventually having to charge up these things?
So with our preliminary lookup of this, we're talking about batteries and sensors and all this other stuff connecting, and the data that we've looked at so far is saying that's going to be a few years that this battery could last for.
So these are big blocks.
These are
6-foot long blocks. We could get relatively cheap, large battery that a lot of the stuff is low voltage, so we can run. I think one of our estimations was like 46 years for a $30 battery.
So we're looking at that as well as the maintenance of parking garages and lots and stuff like that. Over time, you've got to maintain that. So it's just going to be part of maintenance is just replacing the battery or replacing the block because we also might have newer technology in the future if we can improve on this actual concept.
So I've seen like some mall garages, they have the systems overhead. Why did you guys decide to focus on, I guess, the ground system rather than having sensors overhead?
So the overhead sensors are only for when you're there. There's no connectivity to it, and you also have to install that. You have to have a professional installation. When you have these blocks, you literally just go up, you put the block down, and it works like that.
So I guess they have to be pretty robust for.
You can do outdoor shopping malls as well. I mean, like you don't need a garage for the system. You can do it to anything outdoors as well.
That's another
good
good point.
You encounter weather problems then, like snow or maybe a heavy rain day, but we're going to try to work through that. What's that?
About bad drivers when they just start running into it.
Well, that's the part.
Yeah.
That's the durability of the block.
Yeah.
Is to go over it. Yeah. So it's a parking block. So the durability is we're putting the sensor on the inside of the block, and the only thing that's going to be facing on the outside is going to be that sensor. And these blocks are built so that if they get run over, they're still okay. So we're going to keep that. We're going to keep that stability of the block. We're not going to try to affect the actual stability of the block when we're inserting the sensor.
these, the way you describe it is you just go and put the block down. What, have you thought about like that?
Oh no, they screw them down.
So you can screw them down if you want, you know. There's some sort of security, yes. There's some sort of security involved with if you want to screw them down to the ground, you can.
Bunch of free batteries.
Yeah, exactly.
We'll take into account with like the software end that like if something were to happen when we're damaged, you can skip over it in our line.
Yeah, that's another thing is it'll also point out which one is damaged, so you can go out there and you can maintain that individual one instead of finding out after the fact, somebody pointing out, hey, this is not working.
Or for possible theft, right?
Yes.
Lost something in the system to account for that.